Well, there's a HDMI down there on the end. It seems kind of obvious since everybody has Macs and Macs don't have VGA connectors.
Well, even people who aren't Macs, I've got a Chromebook that's HDMI, and I've got a netbook that's HDMI.
But now I'm going to remove it and insert the traditional dongle. I mean, my laptop sees something because it's detecting a second monitor.
I'm going to step out of the way and let you stop.
All right. We're doing some real problem-solving engineering now.
As I say, I'm not that kind of engineer.
Yeah. Oh, it's doing something now. Oh, there it goes. Okay, so it didn't like the adapter.
Is that you?
Yeah. All right. Cool. Good. Oh, come on, Kyle. I was expecting you to leap over it. Yeah. Okay. Can the people out in Meet Echo Land hear me? Thank you. Can you see the Notewell slide? Okay. Okay, great. Everything seems to be working according to plan. And oh, it got so quiet. Okay, well, it's the appointed time. Let's get going. Please note well the note well. Hopefully this is not the first time you've seen this language today. Anything that you say or communicate in an IETF meeting is an IETF contribution. I'm Aaron Falk, co-chair of the TAPS Transport Services Working Group. My co-chair, Zad, was unable to make the trip. We have, I think, 2 minute takers. Kyle, did you recruit somebody else? No. Oh, I was, but that was before the incident. No, I'm counting on you. Just capture any decisions that we make. That's really the thing that we want to get. Things that people have to do before the next meeting. Can somebody who's active in the working group sit near the microphone and type people's names into the Jabber so that it can get into the minutes and the remote folks can know who's speaking? Thank you, Miria. You can probably, I think you know everybody here. You don't need to move if you can tell who people are from where you're sitting. I don't care where you sit. Okay, first I apologize to the room. I am really sick, so I'm not firing on all cylinders, and I'm going to rely on you to help me not do anything stupid, and just assume that any errors are due to my illness and not to any malice on my part. Okay, here's today's agenda. I've got a little bit of status on the working group. We're talking about a couple of documents that that the group is working on. Michael's going to talk about the transports usage document, which is mostly complete. Stan's going to talk about the MinSet document, which has got a lot of useful material in it. Stein, sorry. See, I told you I was going to be making mistakes. Then what I think is going to be the most interesting part of the day is some design discussions around elements of TAPS API, and then some updates on some of the implementation projects. So just a quick one slide status for the, is it? Oh, yeah, that didn't work for me. One slide status, we published our first RFC. This is the really long, thorough analytical document of transport protocols. Thank you to the working group for everybody who contributed. This was really a big effort of research and normalization. Thank you especially to the authors. I think that this is a great accomplishment. Unfortunately, we moved the goalposts a little bit, and this was originally going to be our first milestone, but actually we added the usage documents to the first milestone. So we haven't really been able to cross that that first element off the list. Let's see. So there's been a lot of updates to draft IETF TAPS transports usage, which we're going to hear about. Gory has a UDP variant of the same document. Is Gory in the room? Rats. Everything's good. Thank you, Stephanie. So we need to finish these documents to cross off milestone 1. Gory, I got some late status which didn't make it into these slides. That the UDP document needs some cleanup, but does we are. You may recall in past meetings we talked about, are we going to fold these documents together? Are we going to keep them separate? Nobody seemed to have any strong opinions. We decided that it was easiest to manage 2 slightly smaller documents than 1 larger document. So they're going to proceed. And so I would encourage folks to take a look at those if you haven't looked at them. So question that we're going to talk about today is whether to adopt the MinSet draft as a working group document. I think we're finally getting to the fun part. Well, the people actually doing the work have been doing the fun part, but we're going to hear about the fun part, which is the implementations of the various TAPS related activities. Okay, so I updated the schedule, which basically meant pushing everything out one more IETF because everything always takes longer than you thought. The goal here is to try to finish the usage documents, get them through last call by July. I think one of the things that we should think about when we're talking about these the documents today is whether that's feasible. You know, what are the major issues? It's always requires a little extra focus to try to. It's not as enjoyable to finish the document as it is to start the document, but we've got to get these things done. And so I think that, so the question in my mind is, you know, what are the major issues that need to be resolved? And if they're just small issues, we should be able to do it by the next IETF. And that's it for my slides. Okay, Michael. Oh, let's see if I can just make this work. Oh, there you go. Here you go. It just does the right thing.
It's just. Okay, hello. There's a quick update of this big document, the usage draft. I'd like to say that from the point of view of us authors, with one pretty small exception that that I found in retrospect, which is this TCP authentication stuff. Except for that, we think this is now complete, in that it captures the protocols that we had at some point agreed that this should cover, which is TCP, MPTCP, UDP, UDP Lite, LATBAT as a congestion control mechanism, and SCTP. So the SCTP thing is why it took so long, because it's a very big protocol. It can do many things, and reading all this and understanding all this wasn't easy, but I have to acknowledge, especially Michael Tixon, who helped a whole lot here. There's quite a large number of new transport features that was added. Here's just a small excerpt of that. Some examples of that would be TFO. At some point we said we're going to only do proposed standard RFCs, but that rule was later changed because that would exclude MPTCP completely, and it would exclude some many other useful things. So this is no longer the case, and TFO is then in. It's TCP fast open. LEDBED is in there. SCTP, this now covers also the end data draft, which I think is pretty valuable for some of the multi-streaming stuff. So interleaving stream scheduling, it covers, there was a pretty big function call even in the original RFC of the 4960 of SCTP that's called set protocol parameters, that just covers many things in one simple function call. But really, you need to investigate each one of them to figure out if they are something that are protocol internals, something that an application should care about or not. So these things are now taken out, and they each are a primitive that concerns things like configuring path switchover, configuring fragmentation, path MTU discovery, send receive buffer size. Some new notifications were added: the send a dry event, for instance, partial delivery aborted as an event, configuring the cookie lifetime value, and the IPv6 flow label. There are many more things that happened in this draft, many wording changes. For instance, I'm not talking about transport features and not transport service features, which was one of the changes that was made at the last minute to the other draft as it became an RFC, and this has been incorporated in these two drafts. It has reduced the length of the drafts a lot. And there was an appendix there explaining to people how they should write their contributions. This has not changed into an appendix that explains how the document was written, basically changing it all into past tense and different style. The sequence of primitives is a bit more logical. I try to group things in a slightly more reasonable way. Combine, for instance, this add remove subflow is quite similar to add remove local address in SCTP. And these things are now put together in step 2, where the effort is to make things a bit more uniform. There is a security considerations text. Thanks to Brian for this. Oh, and that was it. So, I mean, it's just an excerpt. It was a pretty, if you do a diff, you see it's a pretty large update. But that's the status.
So, Michael, what's the TCP auth? How much work is it? Who's going to write it? Are you looking for contributors?
I write it, and it's not much work.
Oh, okay.
It's 1 hour. So I just overlooked it as I made this. So I have to just do this after this IETF or even during the week.
So do you think you're ready to go to last call after you add that?
Yeah.
Excellent. Okay. That's great. Thank you. Gory, would you say a few words on the usage document? I would have put you on the agenda, but I didn't figure out how the documents were related. I didn't remember how the documents were related until after it had all been set.
Hi, I'm Gory Fairhurst. I'm going to say a few words about the UDP usage document. Okay, so the UDP usage document is just the UDP and UDP Lite part of Michael's document when it comes to the survey, defining what the IETF has done. And that has been stable for a while. Michael took the outcomes of that which relate to his document and embedded all the further stuff into the document, so everything else is being consumed, and it's just a document that defines the survey of UDP protocols. So there's probably a good reason for doing a rev to fix references, so we'll do that. Otherwise, we'd ask for working group last call of that at the same time as Michael's document as a companion document.
Excellent. Okay, great.
Anybody got any comments on the process that I might have missed or what happens next?
I have a small comment. There are 1 or 2 things in there that I did not take over into the usage one, which were IP layer functions.
Yes.
Should they stay or should they go?
Should they stay or should they go?
Yeah.
Sorry, end of the day, yeah. Okay, that's
I
not
don't
is that a
know.
question to me? You can ask the working group. Okay, so there are. Okay,
mean,
so
like-
UDP is a funny beast because you send datagrams. You can change every datagram what options you use. When you do multicast, you do a whole lot of network layer fiddling to make the transport service support multicast. All of this is kind of in that document. I'd happily continue it in the document, but I've looked for people to review it because it's had less review than the rest because it didn't get taken up in tabs. So I'm not happy with it remaining in the document and nobody reviewing it. If the working group wants to cut it, that's okay.
So my suggestion would be to make them stand out somehow as being not a part of UDP, but generic IP things, just putting it in a separate section or marking them or something.
Oh, I'll happily do that.
Yeah, maybe the title of the document is UDP and other.
Don't even go on how difficult it is to use UDP. Okay, so yeah, do you want to help me figure out which bits should move, and then I'll implement all the rest?
That's easy, yes.
And could someone offer to review all the UDP stuff as we move to last call? Because if we're going to do a last call, we need somebody who understands UDP to help us review.
Yeah, that would
Are
be
you volunteering?
Tommy Polyapple. So I don't quite remember all the history of why the documents were separate. And I'm just wondering, like, for the purposes of them going forward, how will the documents reference each other other than the link? Like, will they say, like, this is a separate document because it's more about datagram stuff and it's different?
I think that's the documents emerged as separate because we worked on them separately and we had different people to talk to make them happen.
Right. I mean, they are very different sets.
Right, and I think we can make sure that they are. Yeah, it says whatever you think it needs to say because it should say what you said.
Yeah, I think that it was really for manageability reasons that we kept it in two documents. There's a
really
tradition
huge
of
if you
publishing RFCs as suites, and we just tell the RFC editor that we want these published together. They'll get adjacent RFC numbers, and probably put some language in both documents that point to the other one that say this is a companion document that's over here, and the RFC editor will take care of that.
Yeah, and some little summary text in the UDP one of why UDP is special and different.
Yeah. I mean, and just to be absolutely clear, the history of this was simply I wanted to go and talk to apps area people to get some review of the UDP stuff so they wouldn't read all the other stuff. So I went and produced a separate document. We took it there. We were going to merge the two. And then we thought, well, maybe it's actually more useful as a separate document because equally when we publish it, they probably wouldn't read the other document.
So I don't think you got an answer to your question, which is who knows about UDP is going to be able to review this? Oh, thank you, Tommy. Oh, okay. I didn't realize that you were actually you agree. I thought that you were just you were being volunteered, but excellent. So a couple comments for the minutes, Kyle. Both documents are need to be revised and then are going to go to last call. Tommy's going to do a UDP review of the UDP document, and Michael's got to write something on TCP authentication. Sorry, auth. Safe. Okay, excellent. Thank you. There. See if it works.
Yes, hello.
Is it working? Yeah.
It's working, yes. So this is a draft working towards Charter Item 2 that we already have heard about to make the minimal set. So we really want to make a minimal set, as it says at the bottom here. And this is based on the transport usage draft that we just heard about. So the way we are planning to construct the minimal set is to first categorize all the features in the usage draft. Then we need to reduce the numbers seriously. And the way we are going to do that is to take only the features that require application-specific knowledge, and also the ones that can fall back to TCP. And when we have that reduced set, we are going to discuss it because there are some anomalies in there that we have to discuss in order to finally, in point 4 here, construct the minimal set based on the reduced set and these discussions. So the categorization has been there previously in previous versions of the draft, and we categorize all the features from the usage draft into functional features and optimizing features and automatable features. And it's mostly the automatable features that can go away because they don't require application-specific knowledge, so they don't need to be in the API. And then in step 2, we take all the functional and optimizing features, and then we have what's left is connection-related features. Establishment, there are 5 features, including a connect feature. Availability, 2 features, listen and specify which trunks types needs to be authenticated. Maintenance is 18 features, including disable enable. And termination has 3 features, close, abort, and timeout. And then we have data communication, transfer-related features, sending data, for example, unreliably transfer a message, and 7 others. Receiving data, we have 2 of those, receive data with no message boundaries, and information about partial message arrival. And there you can see why we need to discuss this, and we have some anomalies because they don't match. You cannot know about the partial message when you don't have messages. So that's part of the discussion we will have later today. And then errors, 3 features, notification of send failures, and 2 others. So then in step 3, we discuss all this, and just afterwards now we will discuss sending messages but receiving bytes. What do we do about that? We are going to discuss stream schedulers without streams and early data transmissions. And in the draft we also discuss the low watermark, where SCTP and TCP have slightly different low watermarks, and we suggest to offer more general common methods where a watermark doesn't have to be 0, because that's probably more optimal. And then we bundle some quality of service kind of features, like disable enable low extra delay background transfer, and specified diffserv code point field. And for security, that's where Michael said he hasn't finished the usage draft for RFC 5925 as TCP authentication. So again, SCTP does that more fine-grained than TCP. So we suggest to specify that you can authenticate either control information or data information or both. And if you fall back to TCP, then you have to authenticate everything. And also cookie lifetime has to be discussed because SFTP and TCP does it in different ways. SFTP in the client and TCP in the server. And I think finally to be discussed, the packet size, because you have this don't fragment field when you want to do path MQ discovery. And we think that the TAP system, I mean, ideally it shouldn't have to know about paths, but probably we have to give the application an information when the path changes if it wants to do path MQ discovery. So we suggest offers to query maximum unfragmented frame size and to query maximum transport. frame size. Okay, so the final step in this is then to construct the minimal set, and that's obviously where we haven't completed the work yet. In that section of the document, there are four subsections: flow creation, connection, and termination. And when you have what we call taps flows, you would want them to be configured and set up well ahead of the connection and the data sending, because you want to utilize the resources as good as possible. So that's why flow creation is important. And then we have flow group configuration, so you can schedule flows in a group. And then we have flow configuration, and of course, finally, and probably most importantly, data transfers. So that's an overview of the draft as it is now, and then we have already heard if we have to decide whether this should be adopted as a working group draft. Thank you.
Can I see hands of folks who read the draft? Okay. So that's 2, I think. Of the people who have read the draft, do you have opinions as to whether the working group should adopt it?
I have read the draft. I've looked at it. I have probably comments on some of the UDP parts. However, I didn't manage to find particularly strong comments on the other parts. So that means it probably looks good to me. So I expected this document to be like it is. If the working group wants a document in this space, I would advocate adopting it.
Tommy, yeah, I would agree with that. I've read it through twice now. Yeah, I mean, there are certain parts, I think, especially in the discussion area, that we should have more discussion on, which is what we're going to do, because they are the correct conclusions to come to by looking at the minimal set. They seem a little bit wonky sometimes, but so I think it's a matter of phrasing, and we need to like wordsmith that, and what does it mean that this is a minimal set, and where do we go from there? But I think it is a very good thing to adopt because it has the right core in it.
Okay. How about anybody remotely? Does anybody remotely have want to voice on this? Oh, right, the big red. I've never gotten to push this before. All right, go.
Good evening, Chicago. Yeah, do it. It's late. I'm not wordy.
All right. Any other comments? No. That was a total mic drop moment. Okay, you're getting that in the minutes. Okay, so it'll be in the record. That's excellent. Hannes, are you going to the microphone?
I don't. So I have a generic. I'm new to the group, so I don't necessarily understand what exactly you are trying to accomplish. But I have one question in terms of the scope you are trying to deal with. Are you only focusing at the layer of the transport protocol, or are you also taking the security protocol into account? Because one of the things that we have to deal with in our work is with specifically IoT devices is that we always use for all the communication using transport layer security or the DTLS, and there we obviously have that API on top of it for the application. And so anything that would from an API guidance that would touch on that component would obviously be useful for us. And I don't know if you guys have looked into that, or whether that's completely outside the scope because it's not the classical realm.
So my recollection, we've talked about security a number of times. My recollection was we tried really hard to get folks from the security directorate to come and participate so we could build security into this API, and nobody would come and play. And so we decided that we would stick with the stuff that we knew, and would love to collaborate with folks who could write knowledgeably about how you would do something equivalent for security. But that's not the people that are active in this group. So we try and, we're kind of sticking to our knitting. But I don't think, I think it would be a useful thing to have a nice, an equivalent of a TAPS that handled security functions. That's my personal opinion.
Tommy, so part of the area, I mean, we're going to get into this later, but as we eventually transition to like the milestone 3, and we're talking about how do we practically do this, I think any practical like API guidance, kind of what he was getting to, will need to include security. And so we can't leave it out. I mean, this draft makes perfect sense as this is the min set of transport. Would it be possible to have another draft potentially also in TAPS that is kind of like, here is the min set of security on top of transport that we could try to collaborate with them? And if that seems to pan out, it's just like a separate thing, and that ends up being guidance towards milestone 3 as well.
So wearing my working group chair hat, I believe that is, I'd have to check the language of the charter, but that might be a charter scope change, but I think it would be entirely appropriate for what we're trying to accomplish.
Right. To kind of
if
put
we
that into
have
2.
the people who are active, people who know what they're talking about that are willing to come and commit the time, because having people who don't know, talk about security, write about security is not going to do well in the IETF.
Yeah, I mean, I would be willing to try a draft of that, kind of basing on what the min set format is, but trying to include security stuff because I'm working with a lot of security people, and so we could hopefully get the right advice.
So, Hannes, does your presence in the room mean that you have an interest in this? Are you would you be interested at least in discussing a draft, or maybe working with Tommy on a draft to talk about at the next IETF to just see if there's some low-hanging fruit here? Okay.
Yeah.
So I think that maybe what we should do is talk about whether to sketch something out. Let's talk about it at the next meeting, see how it goes.
Yeah.
Oops, now we lost Brian.
Very fast. I was just going to say one point, which is the original TAPS document when we did the survey, it did include the security protocols at the very beginning.
Yeah.
So if people could form an internet draft, it'd be really cool to look at that.
Yeah. Okay. Yes. Thank you for reminding me. So I think it definitely was in the scope. I think we kept the wording fuzzy because we sensed that this was going to be a possible outcome. Okay. Now for the design discussion section. Let me do a quick time check here. So we should be about half an hour in. We're just about on time. Michael.
Okay. Me again with animations again. Proposing something about messaging. So this is looking at what is in the min-set draft. When we did this exercise of removing the things that don't have a fallback, we ended up with various ways of dealing with messages on the sender side. You can configure all kinds of things around messages, and on the receiver, because of TCP, all you can do is receive a stream with no message delineation. And this information about partial message arrival, which is not harmful. TCP is in that sense, it has a fallback, but it just doesn't make any sense when you don't have a message. So what can we do about that? And we looked at ways of handling this, to figure out if this combination of sending messages and receiving a stream can work. The thing is, this is basically the only way to become compatible with TCP. And if we don't manage to become compatible with TCP in the way the primitives work, then a TAP system would just, for many things that you use, just always have to say, oh, sorry, you have to do it in a different way because of the TCP. And if it says that, the more it says that, the closer the system becomes to an application picking TCP or picking SCTP, which is not what we wanted to from the beginning. So to try to minimize the hoops that an application programmer has to jump through, there was an effort to try to see if we can make these things work together. And this is really about only one specific thing. So being able to receive a stream as opposed to a message is about one particular transport functionality, and that's the ability of the transport layer to tell an application on the receiver side where a message begins and ends. So for all kinds of applications that know where their messages begin and end, we don't actually have a problem. And that is the case for many applications. So the bottom line of what I'm trying, or the point I'm trying to make here is that telling a receiver, here is your complete message, this is where it begins and ends, creates a big limitation and is actually often unnecessary. I came up with that. We came up with that thing that we call application frame byte streams, which is the minimum smallest change to the TCP-like API. If you want to make that sort of thing work, you have a TCP-like byte stream API essentially. You can just send and you can receive. That makes it very compatible to what was there. But on the sender side, you can optionally give some extra information about where a message begins and ends and what you want to do with these messages, whether you want to send them unordered or unreliable or whatever. And it may all just fall back to being a reliable byte stream, which is always correct, right? It's just slower, but that's the best effort nature of this thing here. So you would have frames that you hand over, and the idea here is that the limited frames will always stay intact because the TAP system makes that so. And you could have more relaxed rules between the frames, like unordered delivery and things like that. But the receiver app would always get a stream of bytes, and it will have to live with the knowledge that if I get a stream of bytes and if the sender side has handed over frames in a certain way, I'm gonna get these things complete. I'm never gonna get a half frame or something like that. So TCP is just a special case. There are no delimiters in use, and that lets us talk to normal TCP applications even on both sides. So here are the animations that try to explain how that would work in a few cases here. Unordered message delivery with SCTP, the way you would do this, you would have messages on the sender side, right? I showed them with a header, some way of app limited, but it could be that you just know the length. Think about 100 byte blocks. An application that always sends 100 byte blocks, then it's implicit. Doesn't matter how it is, but there's got to be some way of delimiting. And the application hands that over, tells the API where the frame begins and configures unordered. And as it does so, for the next frame, it says, oh, this is where the other frame ends, this is where the next frame begins. Configure unordered, does that 3 times. And then at the end says where it ends, and you get this whole stuff into transport, ship it over to the other side. Order may change in transit. You get a primitive to basically say you just want to receive that as a byte stream, so the application doesn't really see that these frames are frames unless it knows. And but the application, we assume, knows how to identify messages. So SCTP would actually hand these things over as 1, 3, 2. They would just come as a byte stream. You would know where these things begin and end. So if you do the same thing over TCP, what happens is you configure, you tell where the frame begins and ends, but TCP just always ignores that. Nothing happens, right? You fall back to TCP. Same thing as before. And then you ship it to the other side, and it's gonna maybe arrive out of sequence, but the API is gonna hand it over in sequence, right? Nothing bad's gonna happen. It's just, nothing breaks, right? It's just optional information that the sender has handed over. For unreliable, unordered message delivery, to give another example, same thing. We're giving these messages in, send them over. Maybe something is lost. And the point here is that SCTP, if this is an SCTP application on the receiver side, is not handing over partial messages. So partial message delivery is excluded here. That wouldn't work, right? So it's just a byte stream. The application knows where it would identify where a message begins and ends, and it gets 3 and 2. But the primitive it uses to receive it is just like receiving a byte stream, and it could be handed over actually, partially. But it's going to be a complete frame when it arrives. And then, yeah, if you do the same over TCP, you know, again, you have to give all this information, TCP ignores it, you send data over, something's going to be lost, TCP is going to retransmit it, right? And you get it in the correct order, no matter what. So the bottom line here is that nothing really changes. And these were simple cases where a message was fitting into a packet that changed the order. So just to give the point that this would work anyway, you would have assumed that these are larger messages and they would be split into multiple packets. So they would actually go across multiple. Some of these packets would be lost. And this is actually SCTP transferring. So what you have on the receiver side is that you have partially arriving messages, and SCTP can handle that and can decide these messages I'm not going to hand over. I'm just going to hand over the message in the middle as I have it complete. And again, it's just a byte stream. The application knows what to do with it, gets message 2. That's the proposal on how we could handle these things. Okay, so this is a discussion slot.
Brian, you're up.
Hi, Michael. I think we already saw pretty much exactly this set of slides at the PostSockets thing in Zurich, correct?
Sure. Yeah, this room is also Zurich, so we're still in Zurich.
Oh, right. Yeah, sorry. Yeah. That's been messing with me all week. People are like, oh, let's walk to St. Gallen for lunch. And I'm like, good luck. You should have started 4 hours ago.
So yeah, it's the same thing.
Yeah, so it's the same thing. So we actually talked quite a bit about this in sort of the following discussions for PostSockets, we'll be talking about a little bit later. And I wanted to go back, I guess, to slide, actually, I don't want to go back to a slide. So the idea that basically there's application level logic that can handle a byte stream and slice things up. What are your thoughts on where sort of the boundary between the application and some sort of library for that would be, right? Because one of the nice things about having a transport that actually does provide message framing for you is you don't need to pull that particular framing stuff up into your receiver. So another way to handle this is that a TAPS aware application could then on the receiver side have the ability to push down a callback into the library that would essentially say, okay, well, find the delimiters in this byte stream. And that callback would get called if it was pulling things off of TCP, but it wouldn't get called if it weren't, if it was actually dealing with messages that you actually had message framing for. So
you mean like in Minion or TCP Hollywood? It
would be like a Minion or Hollywood, exactly. Right. Yes.
Yeah, that's true. I mean, the point is that this makes it compatible to a TCP receiver. So
on
one side. Right?
What I'm proposing is compatible with a TCP receiver as well. So if you have a TCP sender or a TAP sender and a non-TAPS TCP receiver, then you're still going to get this non-delimited byte stream on the side. This is really just a way to organize the code at the receiver, right? So the receiver already has the delimiting code. Maybe you say, okay, well, I'm going to actually take this framing and deframing stuff is actually a part of sort of the transport library's responsibility, even though the transport library might not know where to cut things up. So if you're sending the TCP, then everything is exactly as you say. If you're sending over even over TCP to a TAPS aware receiver, then the TAPS aware receiver would basically take the deframing code and push it down into the library. And then you'd have the ability to sort of simulate having a fully message boundary aware transport even when you didn't have one. Now, there are downsides to this. One of the downsides is if you have a data representation where deframing requires you to parse the entire data structure, in which case you would have to parse the data structure twice, right? You have to run through the end, so if you're dealing with, for example, CBOR objects, right? You need to get all the way to the end of the CBOR object before you know you're at the end. So you could double work there. So I'm not really sure how to handle that case, but from a design level, this seems a little bit cleaner than basically saying, even in a case where you could get a service from the transport layer on the receiver side that's doing the delimiting for you, you're just going to drop the delimiting. That seems like you're leaving a little bit of benefit on the table.
But who's going to drop the framing if you don't have a taps-aware receiver? You're going to, on the sender side, not include the framing because you know it's not a taps-aware receiver.
Well, no, I mean, you have a taps-aware sender with an application that has framing, and a non-taps-aware receiver that just basically, so if you're dealing with, like HTTP request responses, right? Like there are rules for how you parse these. They're slightly complicated, but there's, it's computable. On the non-taps, okay, hold on. I completely lost my train of thought because it's stupid late here. On the taps-aware receiver, the deframing code would actually be pushed down into the library. So the application's getting these things as messages. And you get the ability to simulate having framing in the transport protocol even when you don't have it. Again, I think this might even just be an implementation level detail, right? So this might not even rise up to a design level.
I was thinking,
okay,
Brian, let me try summarizing your comment, which is good idea. I've got a refinement.
Yeah, pretty much.
Okay, excellent. Tommy, and then Colin's in line, and what? Oh, was Colin in line first? Okay.
Lars was before. Okay.
Hi, can you hear me? Can you hear me?
Yes.
Yes, okay, good. I was just going to say, I think something which Brian said a lot of already. I think the idea is that the on the wire format is unchanged. And what changes is that you push a parsing function into the receiver. So the parsing happens as part of the transport stack rather than in the application. So you don't need delimiters on the wire.
My concern is that if you do this, you need to know that you're talking to a taps-aware receiver, so you need some form of signaling protocol or something to figure out.
No, I don't think you do.
If you don't, it's great, I think. Right. I mean, the point is to be one-side deployable, but...
Yeah, I think the idea is that what is being sent and received is identical, but you change the API at the receiver by pushing the parsing logic into the protocol stack, which gives the receiver then a message-based API and doesn't change anything on the wire.
Right, so yeah, that was the point I was going to come up here and make as well, because I mean it says, I think, quite clearly in all the TAP stuff, the point is not to invent new protocols. We're just trying to change how we interact with them, create them as a service. So I don't think I think your slides are correct. I really like the fact that yes, we don't have to worry about the other side being aware of taps. We can write them as messages. The other side doesn't have to necessarily treat its transport as messages. But so essentially there are two cases.
We can,
if we're doing,
I think I got it.
If we're writing messages and what's actually underneath is truly a byte stream, because the only thing that's supported on the other side is truly a byte stream. All we're doing is saying, I'm scheduling how my chunks of bytes on TCP or in a TLS stream through TCP are getting scheduled relative to each other, because I know that they're mutually independent or I can schedule them differently. And that's cool, and they end up as a stream on the other side. There's no real message semantics. This is just a nice syntactic sugar on top of writing. But if I am doing something that may truly have strong message semantics, because practically the protocol I'm running here, is it HTTP messages? Maybe I want to understand the TLS frames, because TLS has framing, and so I could actually understand the boundaries there and write in frames and receive in frames, because those are chunks. Like there is code on the receiver when you're doing TLS that is parsing out from a stream, delineating the frame, and then pulling it out. If I wanted to, either the writer or the receiver could be dealing with its transport layer in writing and reading these TLS frames, or not. And that's totally fine. So I think it's kind of a false problem. And I think the interesting part of the messages is like, what are the semantics around being able to write them that are interesting, that still fit and degenerate into TCP if we have to.
Yeah. So I mean, if we can make it work, I'm all for it. That's my short answer here.
Yes.
Without requiring to know that on the other side there's a tap system or whatever, right? As long as we can have like either one side doing it, I think I'm absolutely for it.
I think it does work. After our past meeting in Zurich, I played with building a message layer that you can stick on top of TCP, and it's fine. So I think it works okay.
Lars Eckert. So this is the answer to this question is probably this is not in scope for TAPS, but I'm going to ask. So I'm thinking about so if you think about data centers, right, or building large scale distributed systems that want to do really low latency, servers will very soon have lots and lots of non-volatile memory on the memory bus. And the notion that you would still serialize a byte stream has too much overhead, right? So what happens more and more is that you actually want to just replicate memory writes to a remote set of sites as low latency as possible, and they're not necessarily TCP byte streams or even messages. That you basically replicate in a set of memory operations that have some sort of, for lack of a better term, call them ACID-like semantics, right? Or over a protocol that better be as lightweight as possible. Typically, people now use RDMA and IWARP, Rocky, what have you. They all have some issues, and I don't think we're going to be using them that much longer. But is that a transport service that TAPS is sort of looking at, or are we in a world where we think we're always going to serialize into a byte stream and then we're going to deserialize on the other side?
So serializing and deserializing is maybe a wrong way of putting it. This is not necessarily how this happens, right? You would actually have STP handing over a message. It's just it's a semantical way of interpreting what you get.
An application is data structures in memory, and if it wants to communicate it sends a message in a well-formatted format that isn't the same format it uses to operate on, right? And that serialization is costly. And the deserialization on the other side, where you parse the message in order to do certain memory operations, is also costly. So that serialization step, I think, is something, at least for data centers, I don't think we can afford that much longer, unless we put it on hardware, and then it's hidden.
Let me ask you a question, Lars. Are there existing IETF protocols that support this?
Hell no.
Then it's out of scope for TAPS.
Okay, that's what I thought we were getting at, but I wanted to make sure. Thank you.
So we've got several other topics. So could you maybe go quickly, Corey?
Yeah. Gary Fairhurst again. Things that Lars talked about sounded a lot like kind of UDP usage of very bare services rather than the TCP kind of way of doing things. I just wondered whether at some point we had to think about whether that was actually another way of doing it.
To do what Lars was talking about over UDP? To do what Lars was talking about over UDP?
To talk about the way you use UDP, you might set options on particular packets and do other stuff, or just send an odd datagram to do things, or send a whole stream of them, and you've got this underlying strong formatting where the packet's actually the thing on the wire, which isn't true of TCP or SCTP, where you put it in memory and it gets marshaled, etc., into forming things that go out on the wire. Was that? Oh, if you confuse the situation.
I don't know what you're getting at. So this is an effort to try to be, to make a fallback possible, right?
Yes, but fallback to what?
In this case to TCP, we chose TCP because you can't. The fallback to UDP is pretty minimal. You can have, like, in the case of SCTP, you have this completely unreliable, transfer. Then you could fall back to UDP, but for the other things you really can't.
So maybe the answer to the question, the answer to my ramble is that what you're trying to do is allow a fallback.
Right. So I mean, if
TCP.
we would add all the UDP things as they are, requiring that these stay intact as messages, and then you just eliminate the fallback to TCP, which is what it is. I mean, but that's not what we were trying to do.
So you say scope's not right for my comment. That's fine. Yeah, that's okay.
Okay, I'm cutting the line at Colin.
Hi, I just wanted to follow up a little bit to Lars's comment. I tend to think that what we're looking for is a message stream-based abstraction going into the future. But following up from Lars, I'd be interested to understand to what extent security and crypto affect the sort of protocols he was talking about, and maybe this should be an offline discussion.
Sounds like an excellent Barboff topic.
Yeah, he can buy me a virtual beer.
Okay, Tommy's next. Okay. And one of these proprietary.
Great. So I'm Tommy, and I'll be talking about, or hoping to start a discussion about kind of the multi-streaming API aspect of TAPS and how we can expose multiple streams in cases in which it's potentially degenerate and we don't really have multiple streams, and how do we express APIs in a clean way when we do have transports or quasi-transports that are supporting true multi-streaming. Next slide. So also, I think the MinSet draft has comments on multi-streaming, and so those authors can bring those points up as well. All right, so as far as protocols that explicitly use multi-streaming, SCTP has functionality there. HTTP2 and Quick have explicit multiple streams, stream IDs within them. Those aren't part of our MinSet or usage documents, but they are effectively being used as transports. And so any API that is dealing with a TAPS service does need to take those into account. And I think those are some of the more interesting use cases that are being deployed right now that have multi-streaming in them. But then there's also a category of things in which we have quasi-streams. HTTP1 can kind of be done as streams. If you imagine that pipeline to HTTP1 requests and responses are kind of back to back, and they have a semantic of, I know which one's a reply and response to each one. So they're kind of separate streams, and they only each have one or two messages, and it's kind of a boring stream, but it's still a separate multiple stream. And because I come from IPsec, I would consider that, ICE and ESP are kind of multi-streaming over UDP. We can potentially, hear me out. I mean, you can potentially have multiple things that are happening on a single UDP socket. You have your control messages, you have your various encrypted flows under different SPIs, and there's a layer that is demultiplexing them and is, in essence, doing multi-streaming over UDP. And it's a tunnel and it's different. But an application that needs to implement functionality could use a very similar model for all of these if we expose it the right way. So that's, I think, kind of a service of multi-streaming that we could be exposing from this layer. So next slide. What is my next slide? Okay, so some of this I had brought up previously in the post-sockets discussions. I can think of kind of three top-level approaches that I've seen to how you do multi-streaming APIs. The first one is every single I/O operation that you do has an explicit option that says, I want to write on stream 1. I want to write on stream 2. This definitely works, and I think it's kind of common. It's very similar to in UDP. I have send to, receive from. You say on every single little message you send, this is what I want to do with it. Not really generic. It's hard to overlay that on top of things that don't have multiple streams. The second option is that you have subflow objects that kind of hang off your master connection. And that is the approach that things like Minion took at least in our original implementation, which kind of went nowhere. So you have your connection API, you bring up your connection, and then you peel off these stream objects and you read and write on them as if they are byte streams or as if they're message streams. And that works well, but there's a very explicit step of I'm peeling off a multiple stream now. And then the last one, which is the one I'm going to try to plug for, is that each of your subflows, each of your streams in your multiple stream environment looks the same from an API perspective as a master stream. They all look like complete peers. And the fact that they are multiple streams that are being multiplexed over some lower level, maybe you can find this out through abstract metadata, but that is not a fundamental part of the stream. So if I happen to open up multiple streams to the same endpoint and they have the same characteristics and they can end up going over the same protocol because I know I have some multiplexing protocol underneath, they can just kind of join silently. Or I can, open up a connection explicitly, but we don't have sub-stream API objects. So those are the three options. I think number one definitely doesn't fit for a tap style. We can overlay this on top of TCP. 3 comes closest to that. The only downside there is if applications think they really want to have very fine-grained control and explicit knowledge about the multi-streaming, they may not be happy having it look like any normal connection. And that is it. So what thoughts you got? I know you had thoughts.
Okay, so Michael, I have a lot of opinions here. So in the basis in the MinSet draft was to say that actually the only thing that matters about multi-streaming in terms of it requires application-specific knowledge is prioritization between flows. And that means that I'm in favor of item 3, I think, where you don't actually see streaming as such. But then you need to have a form of grouping because it has to be prioritization between groups. And then there are these things I called maintenance, and they would apply to groups because if you do something about, say, SCTP, it affects all the subflows.
So essentially you're saying that as long as we have a concept of groups, of
exactly, that's
streams,
as much as you need to expose.
And in TCP you can have a group that means nothing.
And so
you can have degenerate groups.
So that's the thing. I mean, in neat, there is this coupled CC work that I have in ICCIG where, I mean, it's a draft that we have implemented and we have an implementation in neat. So the way this goes in neat is that if we don't get SCTP and we end up with TCP, then we would apply these priorities to different TCP connections. If they share the same bottlenecks, so you could even, you could have things like the flow label increasing the chance of having the same path, and then you can apply different priorities via some combined congestion management.
And for
but
us,
you can just do this transparently, and you don't need to bother the application with it as long as the application says what the group is and what kinds of priorities apply. So that's my assumption here. The MinSet draft also talks about connection establishment and teardown. I think there are certain things that come to that because streams have a certain peculiar behavior in that, for instance, in SCTP, they just exist. So if you expose them like that, right, and you do a connect, that may never be an accept on the other side unless you send data. I think that also matches the quick behavior. You send your first data, and in doing so, you also establish a stream. So that affects the semantics of opening and closing, but I don't think that's a big problem necessarily.
Yeah,
I mean,
right. And yeah, to the point of like how connection establishment and teardown looks, I think in number 3 from what we've been playing with it. If you are implicitly multi-streaming, your first connect on a stream, may do a full bring up of everything underneath you. It could be that subsequent connects are really just open stream commands down below. If the other side, because you were talking about with messages, we can have taps aware or non-taps aware responders. In the non-taps aware responder case, they do their own parsing. but in the taps aware side, they could receive messages directly. I think you have the similar thing for multiple streams, because you could have essentially a multi-stream taps aware listener can essentially have a listen function in which it receives not a TCP stream coming in, but a HTTP2 stream coming in, and treat it as if it is a native stream at its level.
Yeah, but in QUIC or in SCTP, you wouldn't actually, there would be nothing on the wire as it will connect. Only when you start sending data on the stream, there would be something on the wire.
Well,
So this example that,
Well,
I
then it
mean,
kinda looks like a fast
I
open
don't think
connection.
it matters anyway. I mean, it's just an example of something that changes a little bit. You know, there was like, we were talking in NEAT about this time of day server that you would just connect to, and it gives you the time of day and the close. So if you have that kind of thing where the server would be the first to communicate, which I think is really a weird case, that wouldn't actually work, right? You would have to send something to the server to make a request. But I think we see that as a corner case, and I think it is a corner case.
So Colin's been waiting to get a comment in.
Hi, I'm just wondering to what extent this API might be different if we assume there is something other than TCP underneath it. So you know, if you have just a raw TCP connection, that you don't support multi-streaming. You only support multi-streaming if you're running some protocol over TCP. And if removing the option of doing this over a straight TCP connection would change the API and change the decision here.
Right. I think if you can guarantee that you do support multiple streams in your protocol, then options 1 and 2 become more viable. But at the same time, I think it does introduce a whole new set of error conditions and stuff, something you can handle, because let's say I want to explicitly open a new stream, and for some reason I've run out of stream IDs, or I can't do something. So now, like, you have a whole bunch of new semantics that come about because of that. So I guess, what are there any advantages, or like, what are we losing out from on protocols that do support multi-streaming natively if we do an option 3 and just kind of let it be hidden behind connections and do it when we can and otherwise not?
Sorry, 2 minutes.
I'm wondering how I would implement something like RTP over the top of this, where the fact that you're multiplexing would affect the other multiplex streams because it's changing the bandwidth assignments for the feedback, and they're getting feedback on the other multiplex streams. So they're not completely independent. And maybe that just means we should do it at a different layer in the stack. But I can't see how to do this with option 3.
So I'm not familiar with the specific semantics, but I mean, I can imagine also, I mean, if you're doing a whole bunch of TCP streams on the same network, you're also potentially interfering with yourself. I mean, it's a different level, but maybe we could have semantics around that more generically of, I don't want this stream to compete badly with this stream, or it could be maybe like around a group semantic and how do I want the elements of the group to interact.
Yeah, but I think there are some protocols where the subflows are visible to each other. And maybe that just means you shouldn't be using this mechanism to implement those protocols. But you know, the option 3 seems to assume the subflows are all independent.
And I'm perfectly fine with like the implementations of in the protocol stack. If you have something like at your transport layer that is aware that it is doing multi-streaming, that it can talk to the other substreams. This is more just about how is it exposed maybe out to the application. So maybe the application in this case is dealing with a higher level abstraction than it is today.
Yeah, sure. We probably need to discuss this offline, but I think there are some protocols which need more interactions, and maybe they're just not supported. But
Michael,
Quickly, Michael.
just offering an idea. I don't think this is necessarily about the semantics of how we offer the stuff in the API, as long as we can query what happened. So I guess if you were to write such an RTP application over this, and you have a strict need to use this kind of functionality, and the tap system ends up using TCP, is as long as you allow to query that. You do create some dependency, right, which is kind of against the goal here. But then you just probably wouldn't want to fall back on TCP in that case. So as long as you make that information visible in some way, I think the application would just have to say, okay, can't handle it, right? It wouldn't want to run over TCP. But I don't think it's an argument against this way of exhibiting the functionality. I think.
Okay, cutting the line at Kyle.
All right, I'll make it quick. So it seems like what we want to do is abstract away the semantics of the underlying protocol, right? I mean, that's like the whole point of doing this, is to not be protocol aware. So I'm not sure that being able to query about, you know, the specific protocol that you're using is helpful. I mean, and going back to the stream abstraction for a moment, it seems like how are we defining a stream, right? Is it something that I'm not sure that I have a well-defined understanding of exactly what a stream is, in a sense. Like when I'm, you know, if I'm as a programmer trying to create multiple streams for different data streams, that I don't really care which order they arrive in, but I really don't want the, you know, like the keystroke that I'm pressing in my interactive SSH session to arrive after the 4 GB data transfer from the other stream, right? So there are some sort of implicit assumptions that I have about how the stream should interact, and I don't think that a transport service that decides to serialize all requests over a single raw TCP socket is going to be helpful. Like, that's not what I want, even if I didn't think of that in advance when I was using taps to achieve, you know, to do my transport.
Yes, yes. And I think if in the degenerate case over TCP here, these are separate TCP streams and they do not touch each other. Yeah, sorry, that's the degenerate case.
Sorry, Brian, I cut the line. So it's tragic. Okay, so now we go back to Michael again. I'm going to start using a timer because after my
This is the Michael show.
my catastrophe at the last meeting, I'm all right.
This should be a shorter one. Let's see. It's about early data transmission. So also something some strange thing about it we found in MinSet. So looking at this, there are transport features when, you know, as a result of this exercise in MinSet that require, well, I mean, we kept the ones that require application knowledge and allow fallbacks to TCP, and that means that we have 2 different ways of sending data early, actually. We have TFO, which is you send something early, and there is this semantic that there is a slight chance that you get a duplicate. And then, at least in case of the MinSet, we considered SCTP, where you also have a way of saying, I want to hand over data early, but that's different. It means that it comes with the cookie echo, which is a part of the handshake, and it's not going to be a duplicate. Then there's also this functionality of TCP that's not really in the usage draft, because actually it's not very explicit anywhere in an RFC on how this would be exposed in an API, but everybody knows, I think, that you can send data on a SYN without TFO, and then it will be just the first data to arrive when the handshake is completed. So that's also a way of sending a message early, right? You have these 2 ways of sending messages early, like slightly early. You know, we have so the way we've done it is we suggested to call it before the handshake and during the handshake, or like before establishment, during establishment. And in our suggestion, we allow a flow to be created before you connect. You actually have to create something so that you can configure it. which will guide the tap system, for instance, to do happy eyeballing accordingly, because you need to know some things. I think configuring things before you even try to connect can make sense. And then you can, before you try to connect, hand over a message and say whether you prefer to hand it over before or during the establishment, right? So it would be something that as soon as possible, but maybe as a duplicate, or soon if possible, but really not as a duplicate, because I think these are cases that we have to differentiate. And another thing that we have to talk about, which isn't really in the protocol APIs, but you need to be able to query about the maximum amount of data that you can possibly expect to have transmitted, right? So without any guarantee, but something that you possibly can expect that the protocol would actually transmit early, because obviously in case of TFO it has to fit in the SYN. It's like kind of implicit in programmers' knowledge that people just know that, okay, this message has to be that size because of how big my packet is. But in a tap system, it's different. You may have SCTP, you may have QUIC, you may have whatever, and the size is different for every protocol. So I guess you need to be able to query for that. That's the proposal. It's pretty much a dialogue here.
Tell me. I don't know, I think this works. I don't know if I agree that it's probably the best way to expose fast open style data. And so I'll have a counter proposal, and let me know if this works with SCTP stuff. Because you're saying that if you prefer it either before or during, and clearly there are problems because sometimes the protocol won't be able to do something before, and you may send a whole bunch of stuff that is impossible to send before.
Yeah.
So, I mean, in general, like an application, the reason that they would do, at least on TCP fast open, is they just want it to be faster. And they don't really care when it gets sent, as long as it's as fast as as fast as it possibly can. So, I mean, the semantics that we had been playing with were just marking a given write as idempotent, because any fast open data is required to be idempotent.
Yeah.
And so if we communicate that about the write, that is a very passive thing that allows the transport to do whatever it wants with it. And I guess it's the kind of the assumption that the transport, if it is able to send the data sooner, will, unless there's some other reason to slow down data explicitly, so that if it is safe to send the data with the SYN, and the data is idempotent, then that is enough to imply.
Okay. So all right, copy. So that you would then fall back to the case of having it on the SYN without TFO if TFO isn't there, and
right.
That's still correct.
Right, and then that would also apply to data that you send in a TLS 1.3 session resumption. That would apply. I'm not sure how QUIC is going to play into that, but let's say QUIC is ending up switching what path it's going on, and is this data safe to be potentially resent a couple times and stuff like that. So it seems like that may get us a little bit further as a semantic.
I agree. I mean, that just simplifies that more.
Yeah. Anybody online want to comment before we move on? Brian was in line, but he got out. Okay. Thank you. Hi. There's that one right there. Yeah.
So this is the draft of the Happy Eyeballs draft. So basically the motivation here is that the TAP system basically aims to decouple the transport services from the choice of transport services by the application from the choice of the transport protocol and the wire. So Happy Eyeball basically allows to exploit this decoupling and to do a selection of the transport stack based on finding out what is the most appropriate transport protocol from what is available and what is feasible among the given transport protocols for a specific set of transport services. So instead of application having to specify a specific transport protocol, the application would specify a transport service or a set of transport services, and then what Happy Eyeball does, it basically goes through trying to find out which of the transport protocols that fulfill this transport service actually work on the wire. So the background of this, it basically builds on the previous work that was RFC 6555 and RFC 6556. So these are for the doing some sort of happy eyeballing between the V4 and V6. So we extending that to include the happy eyeballs at the transport level. The key here is that we don't only do the happy eyeballs of the transport protocol, but we basically do the happy eyeballs of the entire transport stack. So it could be V4, SCTP over V4 or SCTP over V6, and not necessarily a single transport protocol. And this happy eyeballing comes based on a dynamic set of selections of based on set of policies that we set on the system, and also based on what we learn from the network characteristics when we try connections over time. In the draft, we propose a happy eyeballs framework. Basically, it's got 3 components. First component is the TAPS API. Basically, the application specifies what transport services it wants from the TAPS API, and then the TAPS API would consult with the module that is called the policy management. So the policy management is system-based, and the policy management basically module creates a list of candidate transport solutions. And then this list is passed on to the transport probing component, and the transport probing component basically does the happy eyeballing on the wire and attempts each of the transport solutions and see which one works. And then it waits for one of the connections that it deems to be the most appropriate to win, and then it returns the results returns the handle to the application. So basically, there are some design and implementation considerations how the candidate list generation is pursued. Basically, we're looking at all available transport solutions, or we're looking at certain preset policies. These policies could be set by a network administrator or by a user or by an OS developer. So it could be some system-based policies that derives the decision-making process. Also, it could be based on what we learn from the network in addition to those policies. If we tried a certain path and on a certain end node, and we realize that, for example, SCTP doesn't work on that, then we already have cached information of that path for that specific endpoint does not supporting SCTP, and the next time we don't include that in the transport in the list of transport solutions. And so these outcomes are being cached, just like the same way that is being recommended by RFC 6555. We could also optionally cache other information when we try different transport solutions. For example, the RTT or patent view that would derive the decision makings of the policy. And also we could basically do the concurrent connection attempts in the different ways. It could be based on threads or based on event-based libuv stuff and so on. So the draft goes on presenting what NEAT does with regards to the happy eyeballs. So it also, as an example, basically the NEAT keeps 3 components to generate the candidate list of the transport solutions. It's the policy manager, which basically derives the whole candidate list generation process, and also you have an information base that stores the different policies in it. So we call it PIP, or policy information base. And then you store the network information base based on the per interface or per endpoint in the characteristics information base, or SIP. And you can see it in the diagram how it works. I'm not going to go through the whole sequence here, just for the shortage of time. And it also caches the outcome of the connection attempts. Also, it is event-based and callback-based based on libuv. And so basically, the content of the draft is that it goes to the problem statements, it explains how the framework works, and it also explains how it's done in Neat. And any questions?
Could you talk a little bit about the state of your implementation?
So what I presented here is all implemented in Neat, so it's on the GitHub. And that's actually my next presentation, so there's more of that coming.
Okay.
So if you just go to the, if there's not any question
I think
on this one.
Colin's got a question.
Okay.
Hi. Not so much a question as a comment. That this is starting to look a lot like ICE.
Like what?
ICE. The Interactive Connectivity Establishment Working Group. And the extensions they have, I think, are things which you will need to do with NAT probing. So I would strongly suggest you look at what that working group are doing, even if only to sort of align terminology. But I think conceptually you're implementing something very similar to what they're doing.
I see a lot of puzzled faces in the audience, but that your comment makes perfect sense to me. So does somebody want to ask Colin for?
I mean, just
So let me see if I can paraphrase what you just said, Colin, which is that basically the notion of sort of probing what works end to end is what you do when you're behind, nets and you're trying to figure out, how you can connect and what your addresses are and that sort of thing, right? You're doing a lot of sort of collecting of information through, probing and heuristics.
Yes.
And so, we built protocols that do that and have learned some lessons on, how not to do it.
Yes.
Is that a fair summary?
Yes, if you look at what ICE does, it does a set of connection racing to do NAT traversal, and it's got a policy database to decide which order to race the connections in. So it's got all the components of the system you're building. Now, the details are very different, but conceptually it's doing something very similar. We should learn.
You're not saying that that's a potential solution. It's just a similar project that could be learned from.
Yes, and for UDP, it probably is the right solution for this, but it doesn't work so well for the other protocols. What the ultimate long-term goal is probably a combination of what they're doing in the ICE group for NAT traversal and the happy eyeball stuff for connection racing, because they're two aspects of the same problem.
yeah, it seems. I think my impression of when we talk about happy eyeballs for the connection racing is a little bit higher level, and maybe the protocol that's underneath that we're racing itself could use ICE or other strategies, and sometimes it's a much higher level fallback between two very different options that we do. And the one comment I had was also, it'd be great if the document could go more into kind of like what's the actual algorithm for scheduling the fallback between these, or how that should be done. It seems like the approach is do it simultaneously oftentimes, and it provisions for a little bit else, but then it says, learn from what happened and just do one after that. When we do happy eyeballs for addresses, we often still leave all of the options on the table and try to come up with, what's the right timing scheme to fall back between the options. And so we've done some playing with falling back of whole protocol stacks between different protocols. And it gets tricky because it's hard to know when you cut off the race, and maybe you need to keep track of how far any given protocol stack has progressed. And if this one has gotten 3 levels up and this one got 2 levels up, how much longer do you give the one that got 2 levels? So there's a whole area that could be explored there. That'd be great to get into.
So the way it works in Neat, at least, is that we've got a prioritized list, and these priorities are translated into certain delays. And then you could just try the one that has the highest priority, and that, of course, is driven by your policy. What is the best protocol that you prefer to win? And then you just try that first one. And then after a certain period of time, then you try the next candidate solution and others, so on and so forth. And that's good in a sense that you're actually saving resources by not trying a lot of things. You're not bursting the network with all different options of if your list of candidate solutions are large, then you really want to save resources. Yep.
Hi,
This will be the last comment.
Felix Weinrang, University of Münster. Are there any considerations how to handle early data transmission with API boards? For example, if I write an application requesting or carrying a HTTP request which fits in the SYN, and I open several connections, TCP, SCTP, over IPv4, IPv6, I burn so many resources on the server side. Is this within your considerations of this draft?
So we haven't looked into that, but I mean, I don't think we have explicitly discussed that, but it's something that we can look into. I mean.
Thank you.
Okay, thank you. I think that you've
got another one.
Yes. Hold on a sec.
So basically, now I'm presenting what we're doing at the NEAT project. So the NEAT project started in March 15, and you can see we are a European project, so we are all over Europe, mostly in northern part of Europe, where the weather is not so good. And so we're building a TAPS-like prototype system. And so the NEAT library is basically a protocol and platform independent library. It's open source. It's based on the BSD license, TreeCloud BSD license, and is implemented in C. Currently, we're supporting FreeBSD, Linux, Ubuntu, and Mac OS and NetBSD. And it's a callback-based, libuv-based library. Most of the core components are right now in place, so we've implemented them, but we still got some work in progress to do. The first presentation of NEAT API at the IETF was in IETF 95 in Buenos Aires. And since then, we have done a lot of work. And the NEAT user API, which sits on top of the NEAT library, is based on the TAPS transport usage draft of this working group, plus a set of internal use cases that we have had in the project from our industry partners. And so the key features, first of all, is the API properties. Basically, the application specifies what it wants in terms of services from the library in some sort of a list of properties. And that basically allows to have a control over basically to be able to specify a lot of different things and also to automatize the stuff. This is done using JSON and based on a key value based property format. So you can see on the right side how this the syntax looks like. And this JSON format could have different types and metadata attached to them. For example, in this case, we could have a precedence. And all of these properties, what application requests, can be just done, passed on to the library using one API called NEAT_set_property. So you specify a JSON string, and you specify a NEAT flow and the context, and then that all goes into the function NEAT_set_property, and that's all done. So what precedence means in that term is that if it's the precedence 1, for example, in this example of TCP and SCTP, in case of the property being the transport, then it means that it's desired. So you desire either TCP or SCTP. And that means that try it, and if it didn't work, then fall back to something else. And if the precedence is 2, which means it's required, which means that you fail if it's unsuccessful. So that's how the property system works. And these properties are going to a system called the NEAT policy system. That's how it looks like. It's got 3 components. Basically, the component that sits on top of all of others is the policy manager that basically derives a list of transport solutions. And the policy manager looks into something called PIP, policy information base, that has a set of policies in it. And also the history of the network and what happened on the interface, what happened to a specific IP address, if HTTP worked, if other protocol worked, what was the RTT, and so on and so forth in the characteristics information base or SIP. And policy manager basically consults with PIP and SIP before making the list of the transport solutions, and eventually it returns the list to the happy eyeballs, which is here is called the connection selection component, and eventually the happy eyeball returns the handle to whatever that won the competition. So here you can see that we've got a very flexible way to define the policies. Also, we have a notion of a profile. So what these profiles and policies are basically based on a set of need properties that are prioritized, and is again in JSON format. It can be set by the user or system administrator or app developer or OS developer. So, for example, in this case, you see an example of a profile. Profile is the same as the policy. The only difference is that it's done. The profile is applied before we're looking at the network characteristics of the SIP lookup process. It's a bit more high level than the PIP, the policies, and basically, in this case, you can see the example of a profile. It's called low latency, and if there is an application request that called low latency precedence 1 and the value was true, then it translates into a set of other properties that is called the interface latency between 0 and 40 millisecond. Precedence 2 means that it's compulsory to get that. If not, then you fail. And you use a wire interface with precedence 1, preferably. So that's an example of a profile. And these are all stored in the PIP. And so basically, NEAT allows us to basically code much easier and simpler than the socket API. It has a lot of things built in already in the library. We've got address resolution, buffer management, encryption, connection establishments, and handling all built in inside NEAT. Address resolution and connection establishments are done only with a single function call called NEAT open. And as an example, it takes around 42 lines of code, source lines of code with the NEAT API to basically write an application that listens to a socket. Whereas it takes 59 lines of code to do that with the socket API. So it's already a level of code reduction and simplicity. Also, we ported an HTTP2 implementation of a web server and client that is called the NG-HTTP2 to use NEAT, plus some other applications. And we saw on the average, there were around 20% reduction in the code lines when we use NEAT. So in addition to that, when we have transport protocols, underlying transport protocols that do not provide a specific feedback, whether they work or not, they don't provide the signaling underneath, then we don't know actually a transport like a UDP works or UDP Lite works or not. So we need an application to be able to provide a specific feedback. And the NEAT allows that. It allows the application to say whether it's happy or not with the transfer. So we call it, we have happy eyeballs for the transport, and now we have happy apps. So as an example, a showcase of that, we did the QoS fallback with the UDP Lite using the happy apps. And also NEAT allows you to basically derive a set of appropriate DSCP code points based on the policies that you have and user requirements and dynamic informations that you have collected from the network. And we think that this is an advantage because the main problem that we had for a long time is that the use of DSCP was always limited because we didn't have a high-level API that could actually, leverage that usage. So we think that that's the way forward for the DSCP with using NEAT. So what we did with the case of the Happy Apps example, we use an application that is called the GStreamer. It's a pipeline-based media library for the audio video. And in that example, we made it to work with Neat. And in this example, you can see that it was using the DSCP code point of expedited forwarding 46. And of course, we set up a router that basically drops that. And then the application can say, I am unhappy to the library. And then you basically fall back to using a DSCP 0. So that's basically a fallback mechanism.
3 minutes, Naeem.
Yep, I'm almost done. Okay. So there's been a lot of other updates since IETF 95. We have added the multi-streaming in Neat, so it's now transparently uses SCTP multi-streaming is a compile time option. So if you choose it, you get it. Then we are able to prioritize data transfer between the Neat flows within a certain group of flows that may share the bottleneck, or that you can assign in the API. If you get TCP, you will be automatically using the coupled congestion control based on the TCP/CCC draft. And that's if you get TCP and if it's supported by the kernel. And we're currently working on doing the stream scheduling using SCTP. Also, we have improved the Happy Eyeballs code. We presented it in the IETF 96, some results that we had with the cost of Happy Eyeballs. Also, we use the priorities among the candidate transport solutions as I explained, and the Happy Eyeballs platform is explained in that draft that I just presented. So we support Datagram, UDP and UDP Lite. We support SCTP and SCTP over UDP, both in kernel and userland is already integrated in Neat in the userland. Also the server-side Neat support, that it listens to all different protocols on the server side. Multi-homing support with SCTP and multipath is ongoing. And also we've got security, TLS over TCP, DTLS over UDP, and we are working on integrating DTLS over SCTP and lots of other improvements, debuggings, and coding optimizations. How many minutes I have?
1.
Good. I'm just gonna stay silent here and watch this slide. So, so that's our website. We are at the GitHub, so feel free to issue, comments and feedbacks and submit patches, test results, and suggestions. We've also got an API documentation and tutorial. You can read it, and there is a paper coming in the IEEE Communication Magazine. It will be published in June 17, but a pre-print of it is available on the Neat project website, so you can read it. And that's all. How many other seconds I have?
20 seconds.
20 seconds.
We've got time for a quick question if anybody has.
Yes.
So I have a quick question, which is, so the endpoints are going to be discovering a lot of information about what protocols do and don't work and between different endpoints. Have you given any thought to taking advantage of that information? Sharing it, or otherwise, allowing it to be in the MapRG, there's been a lot of discussion of that, right?
So you mean sharing it with other Neat entities? So,
or centralizing it. So one of the things that the ECN measurement work enabled was to communicate to operators. Like, you may not know that there's stuff in your network that is actually blocking, valid standard protocols from working end to end. You're going to be, you're going to be discovering a lot of that information as more Neat endpoints are doing this kind of probing. Just wondering whether that's a part of the scope of stuff that you're thinking about.
So if I understood you correctly, you're referring to sharing it like to the community, or is it whether it's supported in the system to kind of share?
I'm just asking about the general issue and whether you've given it thought and whether it's something that you guys are looking at. Any kind of, you're doing measurements, right? You're not just building end systems, but you're doing measurements. Well, you're doing anything with those measurements.
And as we begin to test more with Neat, so it's already, I think we haven't arrived to that stage of doing large scale measurements with Neat, but as we move forward with that, I think it's possible to do it.
Okay. Thank you.
But
No,
not, we
Corey,
haven't
do you have
done
a question?
anything as of now.
I could make a comment on that. Within the NEAT architecture, Gori Fairhurst there speaking as someone who plays with NEAT, that there's something called the characteristics information base,
Yeah.
where we collect information about completion of flows, including kind of what happened to the flows and what protocols it got assigned, etc. So the notion of collecting this, I think, is fundamental to the whole idea.
Yep.
Now, that's not something we'll be able to build on a lot, I think, at the moment, but it's sure got to be in there. I remember the BOF for TAPS, Marie-José Montpetit, talking about the idea to be accountable for the decisions that are made when you do the happy eyeballs and other things, and making that visible is such a useful thing, because normally it just gets hidden away and nobody ever knows what decisions were made on the network. So
Yeah.
I'm saying I like the idea of collecting this information and making it available somehow, at least to the user.
Yep.
Okay, thank you. Tommy?
Okay, I'm Tommy Pauly again from Apple. But in this capacity, I'll be trying to present the work that Brian and Miria and Colin and I have been working on, as well as a bunch of other people. We had a group in Zurich to talk about this. So this is the post-sockets API effort, and I think it's, of all the things, trying to jump ahead and say, if we put all these things together, what kind of API do we want to see going forward with this? So here are 4 initial observations and principles that we're trying to tackle and make sure that we have. So we talked about messaging already. So applications essentially deal in objects. A lot of them are written to deal with TCP streams now because that's what they think of. But on top of that, they layer objects. So that should be a native part of the API. Networks are starting to become more multipath. We have more multipath APIs and protocols. That needs to be baked in. That is definitely going to be the way of the future. We must have security. I think that's a good reason to bring security protocols into the TAPS discussion, make sure that we have that. Anything that we're proposing must be able to support security beneath the API natively and not be a tack-on option later on. And then, of course, the APIs have to be inherently asynchronous because we don't want our various messages blocking each other, and it's just the right way to write your programs. So I have 3 areas that I want to cover. So what I'm going to try to do is quickly go through all the parts of the draft, and there's a lot of stuff in the API, so I'm going to try to go at a fairly quick pace so that we can have some discussion about it. But this should give an introduction to what the general proposal is. So first, let's start out with what are kind of the fundamental objects that are in this abstraction for the connection. Here's a top-level picture. I'll go in depth on each of these, but essentially you have a carrier, which is the entry point for connections to send their messages, and then there's a bunch of things around it. So first, what is a carrier? A carrier is a message carrier. This is the primary way that a given application will interact with networking. It sends and receives messages. You can create a carrier by giving it an optional local endpoint that you want to come from, the remote side that you want to talk to, and some context about how you want to connect to it. And so the way to think of a carrier is that it represents some bidirectional flow of messages that you can interact with. This does not necessarily mean it's one transport connection. As we went before, this may be a stream of multi-streaming. This may have multiple connection attempts underneath it. It may be multipath, but logically to an application, it is one set of messages back and forth. So I said that carriers take a local and remote. What are those? These are objects that represent the endpoints. In the degenerate case, this is just your address and port that you normally connect your sockets with, but it includes more than that. It can include all the other things you need to use them. On the local side, here are my certificates that I need to use. On the remote end, it may be an address. Hopefully it's a host name. Maybe it's a bonjour service that I want to connect to. It may be a URL, and it may have requirements for the security that I want to see on the other end. It's our sock adders +++. And remote endpoints can be resolved from one form into another. We start out with host names, they become addresses, that's all internal, but it's kind of one big family of objects here. We also had this thing that we created carriers with, which is called a policy context, or just a policy. And the policy context is essentially the parameters that modify how I want to make my connection. This can be requirements that I have about what is my local interface, what's my local address, things that I prohibit using, what protocols do I support. So I think kind of in the neat context, if I want to say, oh yeah, I want to be able to race between these things or find me the best thing, I turn that option on here. Do I have options if I need to use a specific protocol? What is it? Any other metadata? Yes, Hans.
On the previous slide, so in many of our cases, the configuration of the security options is sometimes quite complicated,
Yes.
and it actually happens in a couple of phases. In the first one is to indicate a couple of different preferences the client has, and typically also along with some configuration parameters. So obviously certificate, if you use certificate-based authentication, but it's different types of certificates that you, for example, trust anchors, you provide your own certificate, different cipher suites, you use algorithm preferences and so on. And then later on, you actually get to see on like what has really been selected. There are also some various configuration options as well that are related to the protocol, like DLS options. So there's a lot of things to configure and to indicate how do you actually deal with any of this.
Right. So, this is a little bit more abstract. One of the things, so Neat has an implementation. We also have kind of a very similar implementation to this in our own stack. And you're right. There are a lot of complexities and things that mess up the purity of this model. So there's a category of things I think that we can say at the very beginning, like here's my minimum maximum cipher suites, or the kind of the preferences for what I'm willing to negotiate. But then during the establishment of TLS, for example, we often have to kind of call out to some delegate that has information of how to look up in a trust store or how to evaluate their certificates. So perhaps what the thing that we set on this local is really just a delegate object that points you to, here's how to access my keychain, here's how to do all of these security evaluation bits. And this is the context that I want to do for that.
Okay.
Yeah.
Get it. And port, when you say port, do you literally mean port, or is that sort of also sort of more on a big identifier? I'm thinking about some of the quick stuff that then survives port changes, or is it?
Right. So, I mean, in this case, on the local side, I guess all of these are optional. These are examples here. So today, oftentimes, I traditionally do have to specify the explicit remote port I want to connect to.
No, to connect to it on the,
sure.
on the
But
destination side.
locally, it's purely optional.
Okay.
Sometimes some protocols I do want to specify my local port. Oftentimes I don't.
Okay. Got it.
Right. Yeah. So I think the key point about these local and remote is that these are somewhat abstract objects and they can be swapped out for different levels of specificity.
Okay.
Thank you. Cool. So we want the policy context. That can also include your security parameters. So then there's an object that is kind of derived from the system, which is called a path. And this is similar to what Neat gets back from its policy manager. The path represents the view of a single route through the network. This is a thing that at any given time, a carrier can use to transmit messages. You may have multiple paths. It's derived from some evaluation or policy manager by looking at the local and remote and the policy context you want. Paths may be different for various apps. Various apps may have different requirements based on the system they're on. Some things are allowed to use cell, some things aren't. That's a classic example. And the path will tell you essentially what option do I have to get off the device and try to do my connection establishment. What are the properties like the MTU? What quality should I expect? And this can help the connection establishment and data transmission do its work. Okay, and then there's an object that we call the transient. It's not a great name, but we haven't come up with a better one. This is kind of a hidden object, but this essentially represents what you would traditionally think of as the socket. And it may indeed be a socket. It's a single protocol instance that's an attempt on the network. It uses a path. It is associated with exactly one carrier, so that as I create, let's say I'm trying to initiate a message carrier out, when we're doing happy eyeballs, what's actually happening underneath is that we are creating multiple transients, and they're attempting different paths and different options. One of them will eventually win, or maybe multiple will win if we have some cool multipath protocol. But that's the relationship there. It is also the top level of a protocol stack. So one of the things that we went over a lot in our design discussions for this was what's the kind of the relationship if you're doing multi-streaming, or if you end up having multiple carriers using the same underlying HTTP2 or SCTP connection. And I think the conclusion was these transient objects that we're racing are unique per carrier. They then plug into a protocol stack, which then may be shared at the lower level. And so that's kind of the wild west of protocols, and those can talk to each other, but there's purity from the transient on up. And then there's one big all-encompassing object, which is called the association, and carriers are a part of the association. These are implicit objects. You don't really have to know that they exist, but this is kind of the larger context that if we have a group of connections that are all talking to the same remote endpoints, if we want to have security session state, if we have cookies we want to associate with things, this is where we can kind of keep that history. And it can hold all of the knowledge that we've had about the various transients and paths and protocols that we've brought up before. And so here's kind of just an example of when we have multiple carriers, they have a transient, maybe they're sharing an underlying protocol connection, and then they're all attached into the association, which is tracking the state that we have about what we know about this local and remote. It has our policy context, maybe it has the security context, so we can do session resumption across different carriers. Great, so those are the objects. The next thing is, what do we do for actually using these objects and sending data? The main model that the draft goes into right now, and I think is probably the right direction, is about messages. So a message is an atomic unit of information that we want to communicate. Reading and writing messages is asynchronous. We can send a message and get various callbacks. We may not have all of these, but options would be, yes, we sent it. Yes, it was after that it was received. Or maybe we didn't send it because something went wrong, it expired. And then on the reading side, I say, okay, I'm ready to read a message. Oh, here's a message, or here's an error. So messages can have semantics when we're outbound that are very special. And this is kind of what Michael already covered. So I could say that I have a certain lifetime on my message, such that if it is expired by the time the underlying transport stack is ready to send it, just toss it. We can have priority independence between messages. We can say that this message must be sent before or after this other message. This message is a high priority. It should get moved to the front of the queue, just like you are right now.
Well, second, the previous slide.
Yes.
Other than the link going down, how long do you expect messages to stick around locally before you send them? Does that even make sense, this function?
I mean, hopefully not too long.
So then, do you really need this?
So I imagine Colin could chime in on this. A lot of this came from kind of like the real-time stuff. 2 seconds or like 1 second, that's
okay,
way too long.
If you have a playout buffer or a...
Yes.
Okay.
And so you could imagine, like, maybe for a normal, like I'm just running over TCP or UDP, I'm just sending as fast as I can. I don't have a local backup, but maybe my protocol underneath knows about how these are being scheduled and says, oh, there's a high delay. I'm going to start dropping these ones that I know will have less chance getting through the network.
So I think we're going to live in a world where you operate directly on NIC rings as an application, and so you don't really have a lot of this stuff anymore.
Fair enough.
Tommy, just a question for the room. We're almost at the end of our slot. Are folks willing to stay here for another 5 or 10 minutes to get through the rest of this talk? Well, if you have to leave, please be quiet.
Yeah, I'll go quick.
Okay.
So we have dependence between messages, jumping the queue. Brian also called this the niceness of the messages, which is a fun term of how nice they are in getting out of the way for other messages. Messages can also have idempotence. This is the solution for doing the fast open protocols, saying that we are allowed to duplicate this message onto multiple transients as they're being attempted. So that allows us to race fast open or session resumption. Yep, so outbound messages can always support all of these properties, even in the degenerate case, because we can just try to locally enforce it. Reading of messages really depends on kind of what the underlying protocol is. Ideally, in a post-sockets API world, if you do have message protocols, even if they're doing very basic frame parsing on a stream, you would always be reading in terms of messages. Okay, so the last section is the connection patterns. So we've already, the one we've been talking about mostly here, and I haven't really mentioned it, is this kind of outbound message carrier, traditional client connection going out to something, or a peer-to-peer connection going out. But that's not the only way we do networking. There are lots of other models. And so the API should probably reflect that. And so here are our attempts at different models we could have. So there's the basic message carrier. The next is the multi-streaming case. So this could be considered a forking carrier. So there are two ways you could imagine the multiplexing working. So the one on the left down here is essentially I just initiate two carriers. They're separate connections, but they happen to have essentially the same association, the same context. There's no reason for them not to share an underlying multiplexing connection, and so they can. The other option is that we fork and we say, I really know I want to open up essentially another stream on this if the underlying protocol supports it. So I initiate one carrier and then I start forking it. For essentially backwards compatibility, we can have a stream carrier rather than a message carrier. The protocol, the draft defines it as you can take a message carrier and turn it one time into a stream carrier, and then you essentially just have a legacy byte stream API over that if your application really needs it. You have the listener model, which is essentially just something that's created with a local endpoint and a policy context, and then it vends out carriers. And so this is kind of like the TCP listener side in which you receive fully connected objects. So what do you do for cases like multicast? This is hard. The attempt here, and this probably needs to be explored more, is that you could have source message carriers and sync message carriers. A source can essentially send to any multicast. A sync can receive from any multicast, but they don't really have strong connection semantics around them. They're a little bit degenerate in that case. There's also a possible model for a responder. So this could definitely be implemented with a full listener that receives full connections, but we believe there is a pattern in which you have kind of lighter weight responders, especially if I'm implementing a DNS responder. Traditionally, I just have one UDP socket and I just receive the messages. So it would make sense for me to have a message responder in which I receive a message in, and then I can just send a reply back to it. I don't have to really care too much about where it came from. I don't have to bring up a full message carrier. You can also imagine this for a HTTP server that just receives a request in, sends a reply, and that's it. It forgets about it from that point. And so that's it. That covers most of the content of the draft. Definitely a lot to chew on and discuss about. So what are the next steps? We want to experiment with more implementations. I think Neat matches quite well with this. We could maybe try to just wrap up the API semantics to say, hey, can we just overlay this, make it look the same? At Apple, we have a very similar model to this, and so we'd like to keep developing that in this direction. Brian has started a Go API outline. If anyone wants to probably help on that, I'm sure they would love more people working on that. So then we also want wider review of this API model, both within the working group and probably other people who are knowledgeable about APIs and all the different protocols that we're trying to stuff under here. This is probably not for just now, but long term, does this make sense to contribute to the milestone 3 of TAPS? We think it could go in that direction. We'd love it too. And then we have a bright new future of no more sockets, and we have messages and multi-streaming and multipath, and everyone's happy. So huzzah! That's it.
Can we we'll probably take a couple of quick questions before we go. Looks like Brian wants to say something.
Good morning, Chicago. So one other ask we have, and this is probably the wrong room to ask this in, is we're looking for people to actually write applications, right? So I mean, like a lot of these, the work that we're doing on the interaction models is kind of initial, and it comes primarily from our experience as application developers, which is, not as much as many people who have written more applications. So we're really looking for wider input on this, because we're looking to learn from really the last 20 years of writing apps on top of the Sockets API in order to do it correctly once more. Thanks.
Any other comments?
I'm Vinicius Fortuna from Jigsaw Google. For censorship circumvention and for privacy, TLS 1.3 is adding like the possibility to have padding on packages, so we can like make it harder to fingerprint the like packet sizes and timing. How would they add padding on a model like this?
So I think that would kind of be up to the underlying protocol stack. Because at the end of the day, the application, it would be great if the application can deal in simple messages, that it doesn't have to worry about the padding or security properties. And we make sure that the connection underneath, that as this message is being processed down through the various layers, because let's say my message is quick or HTTP2, and that goes then into TLS, that layer makes sure it adds the correct padding, etc. So the part of the goal is by abstracting this higher up, we can make sure that there's a common safe implementation of the security protocols underneath. That makes sense?
Kyle Rose. So that, I mean, for things that you can think of, you can do that, right? So like padding is a good example. I would worry about sort of assuming that you can do that generically for all security properties, because there could be side channel attacks that nobody's thought of yet that might be possible, and then the application might need to be aware of them, or the transport might need to be modified to defeat those. So I don't know. I'm sort of wondering how generic that can be, but I don't have a solution for it. I'm just sort of pointing it out.
So just tossing one response out there. As I've been playing around with the implementations for this, I think we can make the API that the app deals with directly be very generic and very general, but then there's that whole underbelly of what's the actual protocol stack. And I think it's really important to make sure that that is flexible. And I mean, quite possibly the applications will be loading their own protocols into there and making sure that as we have new security patches for vulnerabilities, like this is a very extensible modular stack in which we can make sure that the right security principles are being applied. But from essentially the application level of, I need to send this blob of data to Billy over there, that can remain simple.
Yeah, I mean, I think what I'm saying is that so you can make an assertion based on a particular stack or set of protocols that this stack protects you protects the data. The data itself will remain confidential. Like nobody will be able to get access to the bits, a passive observer or an active observer. But it may not be able to say anything about traffic analysis, right? You might be able to say, oh, well, that's a GET request based on, say, the size of the packet if you're not doing padding, or if you do padding, they might be looking at the pattern of the packets going back and forth. So then, the transport might want to introduce chaff into the. It
could.
Right. I mean,
I could load a chaff protocol in as the thing I'm doing post sockets on top of.
Right. Yeah. No, I'm just saying that I think the user, if we're gonna just like we're saying things about the security properties, just as we're saying things about the transport properties like in order, out of order, lossy, lossless, I think we might need to make statements about the security properties we need and then choose the best protocol based on those. But I don't know that we can enumerate all the security properties now. That's something I think that's going to evolve over time.
But that is a good thing, is like if we do this other draft of like security min set, like enumerate the things that may want to be explicitly chosen or advised to the stack. Thank you.
Okay, thank you, Tommy. Thank you, everybody. We're done. Please take a look at the drafts. We'll watch the mailing list for our last call.